Today is day 2 of Taylor Series, and we're going to talk today about what they're for and ways that they can be used. So, picture yourself living, you're transported back in time, 250 years ago. Do you think that would be a nice time to live? No. No internet, no cell phones. It'd be very different. Okay? No calculators. If you worked in a job that required math, you're really stuck. You have no calculators. What these Taylor series do for us, it allows us to use just our heads and simple arithmetic to find values of things that otherwise would be very hard to do. Okay? So, we're going to show you today how accurate you could actually get with this type of activity here. So take a look at the first example. It says use the Maclaurin Series for sine, which happens to be right there, to approximate the sine of 1 radian, so that the error in your approximation is less than 1 over 1,000 without using your calculator. So this is a no calculator activity. It is going to involve error, and the last time we did error was a little bit complicated. This is very straightforward, okay? It's a lot of just looking at numbers and trying to figure stuff out. We need to justify that your error is less than 1 over 1,000, okay? Take a look at this series up here. It has factorials in it, but there's also one other distinguishing characteristic. What do you notice about the signs? They alternate. It is an alternating series. And did we learn a way to find the error of an alternating series? Yeah. Yes, we did. Does anybody happen to remember how you find it? Nicole?
The
next term, exactly. The error is the term after you stop. Okay? So what we're going to do is we're going to write that down as our justification. Since the series for sine of x is alternating, we use the term, quote unquote, after we stop to determine the error. Okay? Since the series for sine is alternating, we use the term, quote unquote, after we stop to find the error. Now, usually in the ones that we did in the past, I would say go out 4 terms, what's the error? And we did do a couple of them where I said find when the error is bigger than that or less than this. We've seen some that look like this before. This one today, because it's got factorials, we're not going to do it with an equation. We're just going to mathematically calculate it. So what I want to do, I'm going to take that off. I want to take this function there, so I'm not writing over it. And I want to plug in the 1 for x. So what would sine of 1 look like? Well, I got to keep that up there. So if x is 1, the first term's a 1, right? Minus. What is 1 to the third? 1 over 3 factorial, right? Do you see what I'm doing? I'm just plugging in a 1 for all the x's, because sine of 1. So 1 to the 5th is 1 again over 5 factorial minus 1 over 7 factorial plus dot, 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 and it just goes on forever and ever. Could you tell me what the next term was? Yeah. Would it be positive or negative? Positive, 1 over 9 factorial. Now my question is, where do I stop so that the error is less than 1 over 1,000? Now notice that all the numerators are already 1s, right? So I need to find which denominator is going to give me a number bigger than 1,000. Does that make sense? Okay. Well, is 3 factorial bigger than 1,000? No. What about 5 factorial? No. You should know your factorials up through 5. What is 2 factorial? 2. 3 factorial? 6. 4 factorial? 24. And 5 factorial? 120. Okay? So 5 factorial is only 1/20th. That's too small. What is 7 factorial? Well, you probably don't know it off the top of your head, but 7 factorial is 7 times 6 times 5 factorial, and I know what 5 factorial is. 5 factorial is 120. What's 7 times 6? 42. Do you think 42 times 120 is bigger than 1,000? Yes. Yes. This is greater than 1,000, so that tells me that the 7 is supposed to be my error term. It says the error term is supposed to be less than 1 over 1,000. Now, I don't even need to know exactly what it is. I just know that it's more than 1,000 on the bottom, which makes the fraction less than 1,000. Let me move that over so you can see everything. There we go. So if 7 factorial is my error term, that means the sum is everything before that. So the sine of 1's approximation is going to be approximately 1 minus 1 over, what was 3 factorial again? 6 plus 1 over 5 factorial was 120, and then we're stopping. So that's my answer. I'm done. I used the series, which is up there. Somebody built it for me to approximate the sine of 1 so that the error is less than 1 over 1,000. That's my answer. And for AP, that's fine. Because I don't have a calculator, I can stop right there. They're not going to make you get common denominators, turn them all into decimals, all that fun stuff.
So I can't leave it as a factorial?
You can, but that's a little more, I'm just showing you it's a little more accurate. It's going to be easier to plug in the calculator in a minute. Okay? Yeah, theoretically you could leave it as factorial. All right? Next question. Use your calculator to find the actual error. So how close is that to the real sine of 1? That's what I want to find out. Okay? So, the approximation is 1 minus 1 over 6 plus 1 over 120. So grab your calculator, put that in it, and tell me what you get as a decimal. So I'm going to turn the lamp on so you can see. I'm going to put my calculator where it works. Come on. There it is. 1 minus 1 over 6 plus 1 over 120. And I get this decimal. When you're dealing with errors, you've got to go out more than 3 decimal places, because a lot of times they're going to match at 3. 0.8416 repeating. That's what that comes out to be as a decimal. It has a 7 on the end because it rounded the 6 after it. The actual answer is when I just type sine of 1 into the calculator. Now what the calculator does, like I told you, it uses these series, but instead of stopping after 3 terms, it goes out like 25, 30 terms and gives you an even better answer. So now type in sine of 1 equals, and I get 0.8414709 blah blah blah. That's enough. So those are the same up through 3 decimal places, agreed? Okay, now the question is, how far apart are they? Errors in this class are always positive, so it doesn't matter which one you subtract from the other, just make your answer positive when you're done. Okay? Now, to get the error, I want to make sure I use all the decimals. So I've already got that answer saved in there, so if I push minus, I can either go back up and capture, if you have an 84 calculator, you can scroll up and get that right there. Now hopefully it'll do it correctly. Oh, I don't think it will. Hold on. I need to go back, open a parentheses, and then go get it. Or if I just get the decimal, that'll work. You don't need a parentheses for that. There's the error. The other way you can do it, if you have an 83 calculator, is just type in the sine of 1 minus parentheses 1 minus 1 over 6 plus 1 over 120 and do it that way. It gives you the same answer. So the error is negative 1.9568 times 10 to the negative 4. You cannot write the E on your answer in the AP test. They want the times 10 because that's what it stands for. Yes, ma'am?
I thought I said it will always be positive.
I know, and I just realized I wrote that down. Thank you for catching that. It's supposed to be positive. Now, scientific notation is well and good, but do you realize how small that number actually is? What does it mean when you do times 10 to the negative 4th?
You gotta go left.
Left 4 places. So I'm going to go ahead and write it in regular notation just so you can see what we're talking about. This is 0.00019568. That's pretty small. So without a calculator, using that fraction answer I got really, really close to the real thing. Close enough for a mathematician 200, 300 years ago to do what he needed to do. Okay? That was actually like 1 over 10,000. Do you have any questions about what we did? This answer or that answer are both correct. Do not write 1.95 blah, 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 E negative 4. That is not acceptable. That is calculator lingo. And the AP test does not like calculator lingo.
So you changed the E to 10?
To times 10. Yes. Any questions on what I did? That wasn't too hard, was it? No. Okay. Now, we have got to put your derivative and integral hats back on because we haven't done those in a while, but we're going to need them today. So I'm going to scoot this up. Take a look at the next example. It says find an in series form an antiderivative for the sine of x squared and then use it to approximate this thing. What kind of integral is that? Indefinite or definite?
Definite.
That is definite. And on a graph, what does that find for you? The area under the curve. So if I wanted to know the area under sine of x squared, you know what? With the knowledge that you have right now, you can't do that problem without a calculator. It's impossible because it has an inner function. U is x squared. Do you see a 2x in that integral for the du? No, you don't. That's impossible. But we can estimate it very well using a Taylor series. Okay? We're going to do it so that the error is once again less than 1 over 1,000 without the calculator. Okay? So, I want to recopy the sine Taylor series. Some of these you're just going to need to know. It makes the math so much easier if you just memorize them. X minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. Turn off that light. Now the first term, you probably remember the pattern better if you write it as x to the 1 over 1 factorial. And notice that sine in its Taylor series is odd powers. And when we built cosine way back when, it was even powers. Okay? Sine is odd powers, cosine is even powers, and it alternates. First term's positive. You can just memorize that. You can always build it. Okay. A minute ago, we plugged in a 1. And we just changed all the x's to 1s when we did the previous problem. Now we're going to take this x and we're going to plug in an x squared. So all it's going to do is change every x to an x squared. Okay? So let's write that down. The sine of x squared equals x squared to the 1st over 1 factorial minus x cubed, x squared, I wrote that wrong, x squared to the 3rd over 3 factorial. I'm adding in this extra step just to show you what's going on. In the future, you can just go straight to the answer. Notice I just changed every x to an x squared and then put the power on it. Now the question is, how do those clean up?
Are they added or not?
That's the question. Do you add those powers or do you multiply them? You multiply. When it's a power to a power, multiply. So this would be x to the second over 1 factorial minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Plus dot, dot, dot. Ooh. Remember I told you that yesterday? If you want a series, you better write the dot, dot, dot. I should have put an equal sign in here. Shame on me. There we go. Okay, could you tell me what the next term is without doing the math? What would the next exponent be? X to the what? 18th over 9 factorial. The power on top is double the factorial, right? Okay. Now, I am supposed to integrate this thing. I'm supposed to integrate this thing. So on the next line, we're going to write the integral from 0 to 1 of sine of x squared dx equals. It's going to be the integral of my cleaned up factorials. So let me scoot this up a little bit. Oh, it's not going to let me. So it's x squared over 1 factorial minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th, 7 factorial plus blah, 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 from 0 to 1. Okay. Now, how in the heck do you do this? Every one of those is just an x to a power. And when we integrate something to a power, what rule do we use? I'll give you a big fat hint. I just told you the name of it. The power rule. Okay? So, before we do a problem, I want to talk about one of these terms. Let's say this is x to the 5th over 7. Let's pretend. I'm just making up numbers. Okay? There's no low D high in integrals. There's not. But the fact that this 7 is a constant, I can bring it out to the side and write it like that. Do you agree with me? Okay? I'm going to erase this in a minute, so you may just want to watch. Now, if I was going to take the antiderivative of this, what do I do with that 1/7? Anything? I just leave it alone. So, if I was going to take the antiderivative of that, the 1/7 would just sit there. Then I draw parentheses, and I put my x. Agreed? What is x's power going to become?
6.
6. What goes in the parentheses? 1 over 6. Agreed? Now, if I was going to put that all back into a fraction, that would be x to the 6th over, now I'm leaving it this way on purpose, 7 times 6, right? They both go on the bottom. Are you with me? I could write x to the 6th over 42 also. I'm going to do the same thing with every one of these. Okay? So what do you notice between here and here? The 7 stayed put, right? The power went up here, and I put the same thing on the bottom. That's the quick way to do it. Okay? So now with that knowledge, let's do this problem. So this will be the 1 factorial. Whoops, I wrote it in the wrong place. The 1 factorial stays there. What does x's power become? The 3. And I put the same number on the bottom. Okay. Minus. Write it again. Put the 3 factorial. What does x's power become? It was a 6.
7.
Now it's a 7. And then a 7 goes on the bottom. 7 times 3 factorial. Plus. The next one, the 5 factorial, stays on the bottom. What does x's power become? 11. And then 11 goes on the bottom. You do the next one. Yeah. Is that what you got? X to the 15th over 15 times 7 factorial? Mm-hmm. Okay. Now, after you take an antiderivative, you put a bracket on and a 0 and a 1, right? That's the next step. Okay. if I plug in 1 for all the x's, all the numerators are going to just turn into 1s, aren't they? Because they're all powers of x. If I plug in 0, what's going to happen? Every single term will be a 0. Agreed? So let's write it out with just the 1s. So it would be 1 over 3 times 1 factorial minus 1 over 7 times 3 factorial minus plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial plus dot, dot, dot. Remember we said the zeros are going away. We plugged in the 1s, made all the x's 1s, and we don't have to worry about plugging in the zeros. Now that problem looks exactly like the one that I got when I did sine of 1 up on the previous problem. Okay? Now my question is, which term is the error term? Not the first one. Is it the second one? Is 7 times 3 factorial greater than 1,000? No, it's only 42. What about 11 times 5 factorial? Is that going to work?
Yeah.
Yes. That's my error term right there. The 11 times 5 factorial, because 5 factorial is 120, and 120 times just 10 is 1,200, and I only need 1,000, so that's definitely big enough. So my estimate for this integral is going to be 1 over just the first two terms, 1 over 3 times 1. You could just write 1 over 3. Let's do it that way. Let's make life simple. I wish I could. I'm going to have to do like, when I do that, can you, is it moving up a little? Yeah. I got to hold it. 1 over, that's what I don't like about this. 1 over 3, and I've got to change back to the pencil. 1 over 3 minus 1 over, what is 7 times 3 factorial? 42. And that is my answer. Sorry I'm down so low. So that's the area under that sine of x squared from 0 to 1, approximately. Now the question is, how close am I actually? Let's see. We're going to do exactly what we did on part B on the previous one. We're going to put that in the calculator. We're going to put that exact integral in the calculator and see how close they are. So I'm going to squat down here. The approximation is 1 over 3 minus 1 over 42. Let's see what that comes out to be. Calculator, light source, 1 over 3, clear, 1, clear. There we go. 1 over 3 minus 1 over 42, and I get 0.309523 dot, dot, dot. That's enough. 6 decimal places is plenty. I have a tendency sometimes to accidentally transpose numbers. If I do that ever, please catch me. I think I got those right. Yeah, I did. So, because I have a calculator, I can actually find that true area. What are the buttons we push to get an integral? Math 9. So now, once you wrote that down, do a Math 9. 0 to 1, sine of x squared dx. The actual is the integral from 0 to 1 of sine of x squared dx, which is 0.310268 dot, dot, dot. Not until the very end. Not until the very end. As soon as I find the error, I'm done. Then I could truncate. Okay, so now we need to subtract those two numbers. So I'm going to put the minus sign that brings that one down. Go capture this one. Subtract them. And I get the error is 7.445 times 10 to the negative fourth. And you can write it just like that. Let me scoot that up. Oh, that's right. I'm on the iPad. I could scoot the whole iPad up today. I forgot about that. There we go. There we go. Totally forgot about that. Yeah, I can just slide the whole iPad up. Yeah. And that's about as small as the last one. It's 0.000007445. But you got to go out at least 3 decimal places beyond the zeros. Questions about what I've done? Anybody? Okay. Either you're all with me or you're all asleep. Thumbs up if you're with me, please. Awesome. Okay. Turn to the back, please. Are we on the screen? Yes, we are. That is the beauty of recording with this document camera. Write the Maclaurin series for f of x equals e to the x. Give the first 4 non-zero terms and the general term. I forgot to do the general term last period, but we'll do it this one. Okay. Now, the Maclaurin series. What does Maclaurin mean again? C is 0. It's centered at 0. Okay? So, if we were doing this by hand, I'm going to just tell you what it is to save time. If I was doing this by hand, I would take e to the x, then I would take its derivative, and its derivative again, and its derivative again, and its derivative again, and I would plug in 0 every time. And what would happen if I did? It'd just be 1. 1, 1, 1, 1, 1. And so the powers of factorial just keep going up. So I can build this one very fast. The function, which is e to the x, is this right here. It is 1, always 1 for the numerator, because when you plug 0 into the derivative, you get 1. 1 over 0 factorial plus 1 over 1 factorial x to the first. Wait a minute. Why didn't I put an x on the first one? Because it's x to the 0. I really could have. I'm going to go back and do that just to be consistent. Plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third. Now, it says 4 non-zero terms. Are all of those coefficients non-zero? What is 0 factorial again? 1. So the first coefficient is a 1, and x to the 0 is 1 also. So we're good. We're okay. We have 4 non-zero terms, because this will be 1, this will be 1/2, and that'll be 1/6. Plus dot, dot, dot. Plus. Now, you're going to need practice with this anyway. This is a great time to start it. Okay. What are the numerators always? 1. What are the denominators always? It's a factorial, and I always start at n, so we're going to say n factorial. And what about the x? X to the n, because the factorial number and the n power always match. So that is what is called the general term. If I said I wanted the 22nd term, that would be 22nd factorial. Yes, ma'am?
How come this one, the plus and minus sign function, like it doesn't change?
Because sine and cosine, because it does this, changes from positive to negative. But e to the x is always positive. That's why. Good question. It's always positive, so every term is positive. Okay? Any other questions? All right. Use your answer to find the limit. Would you like to go back to limits for a while? A little bit easy stuff? Yes. So, we want to know the limit of f of x minus 1 over 2x. So what we're going to do is we're going to write limit as x approaches 0. We're going to draw a big fraction bar. But before we do, or we can do, I think we can do this at the same time. I think you can stick with me. We're going to clean up each term as we write it on the line. What is this first term going to clean up to be? Just 1 plus. What's the next term going to be? 1 over 1 factorial is 1, x to the first, so just 1x. Plus 1/2 x squared, agreed? Plus 1/6 x to the third plus dot, dot, dot. And I'm not going to worry about the nth term. Okay? Now, it told me to write the function and then a minus 1. So put a minus 1 on the end and the 2x on the bottom. All right, now, what's my favorite way to take a limit? Plug it in. Remember, plug it in, direct substitution? If I plug in a 0 for x, what's going to happen on top? It's going to be 0, right? I got a 1, and then a bunch of x's, and then a 1. So minus 1, 0. Over 0, right? 0 over 0 means 2? Indeterminate. Got to keep going. So we learned a bunch of different ways the first week of school. Then we learned a fun way that's faster. LHOP. We're going to do L'Hopital's rule. Now, with L'Hopital's, this is 0 over 0, so we're going to do LHOP right here. Limit as x approaches 0. Now we need to take the derivative of the top. We just took an integral of a series. Now we're just going to take a derivative. It's not that hard. Okay, what's the derivative of that first one? 0. What's the derivative of the x? The derivative of the next term? 1x. Agreed? What about the next term? 1/2 x squared plus dot 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 minus, what's about that last one?
0.
That's a 0. The denominator's derivative is just a 2. Now, before we go any farther, I want to show you something. Take a look at this right here. Take a look at this right here. Okay, would the next term match, do you think? Yes. Why is that? It's not really magic. What are we taking the derivative of? What was the function that this came from? What is this? E to the x. What's the derivative of e to the x? Itself. Because if the derivative of e to the x is itself, the derivative of its Taylor series is also itself. Okay? So, a little bit of an interesting fact to show you there. Now, can I plug in 0 safely and get an answer? I better be able to because the bottom's a 2. What is the top going to be? 1. So the answer to this limit, whoops, I'm on highlight, equals 1/2. I'm done.
Oh, okay, there's a one right there.
Are we good?
Yeah.
Everything else, the zeros and the x's go away. Get 1 over 2. Questions? All right, now let's take a look at the last example, which says write the first 4 non-zero terms of the Maclaurin series for this function. Now, we've written a Maclaurin series for e to the x. We've written one for cosine of x, but we've never done a product of the two, okay? Now, because e to the x has an infinite number of terms and cosine has an infinite number of terms, multiplying them together, no, we don't want to go there. We just want to take and do this one the old-fashioned way. The reason I'm doing it today is because now that we've done a few more, we should be a little bit more adept at doing this properly. So, when you're about to build, always recopy the problem first. E to the x cosine of x. And now you need to put your derivative thinking caps on. What rule, if any, do I need to do the derivative of that? Product rule. Okay? So, f prime of x is going to be 1, which is e to the x, times derivative of cosine, which is what? Negative sine. Be sure to put that in a parentheses, please. 1d2 plus 2, which is cosine, d1. What's the derivative of the first term? E to the x. Okay? Now, if I leave it like that, and I have to take the derivative again, I'm going to have to do product rule on the first term and product rule again on the second term. And when I did this the first time in my notes, I did that. And oh my gosh, it got to be so long. But if you factor out the e to the x, which is what we're going to do, what am I going to be left with?
Negative sine x
Negative sine x plus cosine x. And now I only have two things multiplied together, which means I only have to do product rule once. Okay? So I'm going to box that in. That's my first derivative. Come back up here, box in the original equation. Because as we do these derivatives, it's going to get a little crowded. And it helps to know exactly where the derivatives are. Okay, 1 is e to the x, 2 is the parentheses. So let's carefully take the derivative of this. So 1, just recopy e to the x. D2, carefully take the derivative of the parentheses.
Negative sine x.
Careful.
Negative cosine.
Negative cosine of x
Plus negative minus negative sine.
minus sine of x. The derivative of positive cosine is negative sine. So that is 1d2 plus 2, which is recopy the parentheses, times d1, which is just e to the x again.
Can you pull out another e to the x?
Yes, that is exactly what I'm going to do. Now, without writing it down, I want you to think for a minute, because now that you're getting to be college level math students, you need to be able to do a little bit more of this in your head. Okay? If I distribute the e to the x, if I did, would not every trig function have an e to the x attached to it? Yes. Okay? So I'm going to avoid doing that and turning right back around and factoring it out. And I'm going to factor it out now. If I factor out the e to the x, that's true, the cosines will cancel, but I want to write down everything that's left first. Negative cosine x minus sine x minus another sine of x plus a cosine of x. Now, if you see that the cosines cancel, you can go ahead and do that immediately, but I'm writing this down for those who didn't see that. Does everybody understand how I went from the first step to the second step? Just pulled out the e to the x from everything. And now, the cosines do cancel. What does the inside signs turn into? Negative 2 sine of x, right? So it's going to be negative 2 sine of x, and I'm going to put the e to the x on the end. It doesn't matter which one comes first, the sine or the e. But I would not, it's kind of dangerous to say e to the x minus 2 sine x, because it's not subtraction, it is multiplication. So there's my answer, and actually it's simpler than the previous answer. All right? If I have to have 4 non-zero terms, I must go out at least 3 derivatives. I may have to go more, but we'll stop at 3 for now. Okay? So taking what I boxed, do I need to use product rule on the box? Yes. I have 2 x's in here, so the answer is yes. I'm going to call the negative 2 sine of x the 1, and the e to the x the d2. You do it right now. Do that first step, just the first step. Don't worry about cleaning it up. Okay, when you've done just the first step, don't worry about cleaning. Look and see if you got what I got. All right. Any questions on what I did right there? What can I factor out? Negative 2 and e to the x. So negative 2 e to the x leaves me with sine of x plus cosine of x. Okay. So I have 4 boxes, which should create 4 terms. Okay. So I'm going to draw a line right over here. And I've got to plug in a number for each of these, f of something. What am I plugging in and why? I'm plugging in 0. Why? Because it's Maclaurin. Maclaurin automatically is to plug in 0. So let's be careful. What is e to the 0? Every time you plug in a 0 with an e, it's 1. So it's 1 times the cosine of 0. 1 again. So that's 1. So we're good. We got a 1. That's my first numerator. Oh, you can't see that. Let's zoom out a little bit. There we go. Now let's plug into the derivative, f prime of 0. Plugging into the big box, the second big box. So it's going to be a 1 parentheses. What's the sine of 0? 0 plus 1. So that's still 1. So we're good. Double prime. Negative 2 times 0 times 1. That is 0. Uh-oh. Now that 0 showing up means that I'm going to create a 0 term, which means I'm going to have to take another derivative. Okay? Well, we'll do that in a minute. Let's finish this. Triple prime of 0. So the outside is going to be negative 2 times 1, which is negative 2. 0 plus 1. You can't see? Still can't see. Dadgummit. There we go. 0 plus 1 is negative 2. So we're good there. That one's fine. Okay. Oh, I accidentally made it big again. There we go. Okay. Because we got a 0, we got to go one more term. Now, I'm going to make it big again. I know that puts that off the screen, so just bear with me. Remember that a fourth derivative, you have to put the 4 in a parentheses. Okay. I want you to do the derivative of that bottom box that I'm pointing to right there and clean it up. Okay, hopefully I'm not going too fast for you. Okay, I haven't written the final answer down, but the signs do cancel. What's the coefficient going to become? Negative 4. Do y'all know why it's negative 4? How many cosines are in the middle? 2 cosines. So that 2 right there is going to multiply to that negative 2, giving me negative 4 e to the x cosine of x. Okay? Is that going to give me a non-zero? Yes, sir. So that's going to be negative 4 times 1 times 1, which is another 1. Negative, no, it's not. I was just making sure you were paying attention. Yep. There we go. Now here's the question. Can you build the polynomial?
Yes.
You have to be able to do this for the quiz on Thursday.
Wait, oh yeah.
Oh yeah, oh yeah. Okay, where do all the box numbers go?
They're the numerators.
They're the numerators. And what creates the denominators? The factorial, starting with what? 0, starting with 0. So, f of x, which is e to the x cosine of x, is going to be the following. The first coefficient, 1 over 0 factorial. Is it going to be just x to the 0, or is it going to be x minus some number to the 0?
X to 0.
X to the 0, because there is no, c is 0. It's Maclaurin. Okay. Next term. Numerator. What's the next box number over here? 1. Bottom is 1 factorial. X to the first. Plus. I'm going to go ahead and put the 0 in just to keep my factorials in order. Because the next number is a 0. I know it's causing problems, but I'm going ahead and putting it on there to keep my factorials in order. And then the next one is going to be negative 2, then 3 factorial, x to the third, and then negative 4, 4 factorial, x to the fourth. Okay, so I'm going to clean. What's the first term? It's a 1. What's the second term? It's just an x. Third term is 0, so I'm going to mark it out. What does the fourth term reduce to?
Negative 1/3 x to the third.
Negative 1/3 x to the third. This is negative 4 over, what's 4 factorial again?
24.
24. So that reduces to negative 1 over 6 x to the fourth. And there it is. That is not an alternating series. It doesn't look like much of a series at all. But when you start mixing together functions, it starts turning the series really kind of weird. And that's okay. Now, would I ever make you go from there back to the other? Not that complicated. We are going to go from a pattern back to which Taylor it is. But we'll do that later. That's in a few more days.
Is this on the quiz? Like this?
This? No.
This program?
No.
Wait, this isn't is all the things we turned in or homework on this?
No, just the second assignment. Just the worksheet 2 on Taylor's. That's why I started.
Oh, so.
That's right, you weren't here. The worksheet 2 on Taylor's is the one that the AP practices on, okay? What else was I going to say? Oh, but a problem like this, a simpler problem like this, yes, would be on the quiz. But what I would say different, I would say it would be of degree 4. Degree 4 means you go out to the 4th derivative, okay? Any more questions on this problem? All right, we are done.